My name is Simon Lopez, and now that Josh and David have explained our project and our system, I want to be explaining the analysis on the data. So let's suppose we want to send a signal to the submarine to submerge to 200 feet. We could do this by sending or using a unit step signal with an amplitude of 200. And we're going to be creating different simulations by changing the values for k. So our first simulation here in figure 2.1, it's with the k being equal to 0.45. Now there's a black line here. It's a trace representing the input signal to the submarine controller, and this blue line here, it's representing the depth of the submarine. Now, the deepest it goes, it's 350 feet, which is an overshoot of about 75% of our desired steady state, which is 200. And we can see how the graph it never stabilizes at 200, so it just keeps oscillating and it just keeps going and going. Now this is because after we find the poles of the system, we're gonna see why is that. So to find the poles of our system, we can find the roots in the denominator of our transfer function, and those values are these values right here. After we calculated them and previously shown how to do those steps, these are the values that we have now, and we can see that by looking at these poles, they lie on the border of the positive x-plane, and this making the system marginally stable. And this, you can see it here on the graph, how the system never stabilizes at 200 feet. Now our next simulation was ran at when k was equal to 2, and again the black trace is representing the input signal of the submarine, and the blue trace is representing the depth of the submarine. Now we can see how the submarine reaches the deepest it goes. It's at 275 feet again, which is an overshoot of 35.5%. So half of what it's way better than our previous K value, but it's still taking some time to stabilize. In this case, it took about 8 seconds to stabilize. Now to find the poles again, we can also do it by finding the roots of the denominator for the system, and then we find those values here. These are the values that we found, and by looking at these poles, we see how the system it's completely stable now after those 8 seconds. After those 8 seconds here, so the submarine actually reaches the desired depth that we wanted. Now for the following simulation, we had a k being equal to 10, and we ran it for 10 seconds also, but this time the stabilization came faster now. It occurred like at about 3 seconds, and the deepest it went, it was 225 meters down here, which is 12.5%, and that was a much better case now for the k value. Now to calculate the poles, we can also find the roots of the denominator, and these are the values that we can see right here now. And by looking at those poles, we see how the system it's completely stable now. And by comparing all the previous cases for the different k values, we see how this is the best case we have so far. And after studying and comparing this system with the different gain values, we can see how we can see the importance of the poles of the system. It's pretty much one of the significant conclusions for this project. And every system has a different purpose, and therefore choosing 1k for value might not be the best choice for every different system. And also choosing your gain value is also a factor of cost. So the higher the gain value, the more money that you have to spend on it. So essentially it's a trade-off between the cost and stability. And pretty much concludes our presentation for the 309 project, and thank you for listening.